Okay, welcome back everyone. Happy Monday. Can you believe we're having our second to last class here? And we have just one more chapter, which is on polymers. And I know I've played into this many times. Those of you who are not biology majors, no disrespect to those who are, but those of you who are not have been feeling very much in the minority these last two terms. These two classes are all yours. And really when I say that, of course, polymers are pretty relevant regardless of what your major is. They are, polymers were one of the greatest technological advances of the previous century. And polymers, as we know them, even man-made polymers, are over 100 years old. We'll give some examples of that later on. But think of all the things that we use that are made of molecules of human origin as opposed to natural origin. Probably, well, I guess cotton shirts are still natural, but even cotton is made of a natural polymer. So not all polymers are man-made. But certainly in the medical industry, think of all of the bags and tubes and syringes you'll be using that will be made of polymers. Polymers that are also used in drug delivery systems. It goes on and on and on. So they're relevant, I think, to all of us. And the great thing is, in many ways, I'm not going to have to teach you anything new in order to learn about polymers. We already have all of the information we need to understand it. But polymers, of course, if you want a definition, a polymer is a macromolecule, meaning a very large molecule, that's made up of building blocks called monomers. And those monomers, in some sense, repeat in the structure of the polymer chain. And so our focus on this chapter is going to be what it's always been in all of the other 29 chapters we've studied in this book, which is going to be structure, mechanism, reactivity. And in this case, mostly structure with a little bit of mechanism on the side. And all of it is going to be mechanisms that we already know. I don't think there's going to be anything particularly new. Oh, maybe you might argue that the polyurethanes made from carbamates are in a sense, even those are really not new. They're just another functional group that kind of act like carbonyls, and so it's even going to look like some of the reactions we've seen so far. So even though the carbamate isn't a functional group you run into all the time, or the isocyanate functional group, same thing, I don't think you're going to be able to make the argument that you've never seen anything like this before. I think it will, at least I'll do the best I can to help that to make some sense. So basically today, what I would like to do is get us through one of the two flavors of types of polymer formation, namely addition polymers, which are also called chain growth polymers. And this is all your polyethylene, polypropylene, polystyrene, all that side of life. Think of all the things we use that are made of those things. Think of your styrofoam peanuts, your styrofoam cups, you know, styrofoam is puffed polystyrene. And of course, we also use polystyrene in the not puffed form. Do you know those disposable punch cups that are like if you squeeze, they're brittle, like if you squeeze them, they'll break? Those are made of polystyrene. Whereas the ones that are flexible, that don't break when you squeeze them, are probably made of polyethylene or something similar. But there's all sorts of other polymers. Now, there's certainly other plastics that we drink out of, like Nalgene. I think Nalgene is a polycarbonate, though I could be wrong. Double check me on that. And those are different. Those are condensation polymers, step growth polymers. So we'll learn about those on Wednesday. But I would like to focus on addition polymers today. I do have a couple polling questions for you later on that are going to be on, oh, and there goes the police or ambulance or something. But anyways, I don't know. In a sense, it's been kind of enjoyable to teach from my own house. In another sense, I won't miss it going back to normal teaching this coming fall, God willing, and the creek don't rise. Okay, So we're going to focus on addition polymers today. So let's see. In the rest of, I've also got some definitions here. I won't insult you by reading them to you. Let's see though, there might be some PET, polyethylene terephthalate. You can read a lot of these definitions by yourselves. The first type of plastics that came out, your thermosetting resins or your thermosetting plastics, these are the ones that can only be molded once. And the first type of man-made material like that was called bakelite. Perhaps you've heard of it, going all the way back to 1907. Can you believe that? That was before even I was born. Little joke there. You can find there's some sort of market for antiques made of bakelite. I think they made some jewelry or decorative items out of bakelite. Bakelite's kind of brittle, so it's not the sort of thing you want to drop. The only thing I know about from sort of my own hobbies that was made of bakelite, since I'm a woodwind player, and so you can find really, really old saxophone and clarinet mouthpieces made out of bakelite. And these can go for a pretty good chunk of change. I would far rather have something that was made recently with, you know, machining methods and CNC methods and things like that that are made to very precise tolerances. You don't have to worry whether it's lopsided or, you know, something like that. Well, you still do, but that's another story. So that's just me, but there's a certain amount of demand for these old things that are made of bakelite. Good, so let's see. In order to understand chain growth polymers, you need to remember your radical reactions. And actually, chain growth polymers got brought up in chapters 6 and or 8, way back in Organic 1. And if you had me, I said at the time, well, we'll get to those later. Well, later is now. So since that's part of this, this polymers chapter. So, but one thing to bear in mind about addition polymers is that when you get your final macromolecule, it's going to contain all of the atoms in the monomer molecules. Usually those monomers are alkenes. That's not going to be the case for step growth or condensation polymers, which we're going to get to next time. Those do not include all of the atoms in the monomers because part of the process includes includes condensation reactions. And so you'll wind up making a large number of small molecules, usually water or HCl or something like that, in addition to the polymer molecule. Now, I don't know, I should know this. Do you guys actually do a polymers lab? Because it's possible to make, there are certain polymers that are real easy to make. You can, no, you don't. Yeah, there's certain that are real easy to make. And you can also, if you don't do this in lab, you can certainly find very good YouTube videos on this. There are nylons that are real easy to make. Not the same nylons that are in nylons, you know, in stockings. But, which by the way, oh, if you get on YouTube, you can find some really fascinating video footage from, round and about the 1930s or 40s, maybe even a little earlier than that. I think it's more like the 40s, when nylons first came out. And you can see like whole crowds of women in department stores just going crazy, trying to almost get over each other to get these things. It's just pretty amazing how times have changed. But and now you just walk into you know, Walmart and get whatever you want. But be that as it may, so you can find some pretty good stuff on YouTube. YouTube is apart from getting all your data, right? YouTube is your friend. Okay, so so the polymer you get from an addition polymerization contains all of the atoms in the monomers, and usually one or two other atoms besides. But by the time you have, you know, 1,000 or 10,000 or 1,000,000 monomer units, if there's a little bit that came from the radical initiator, it's a non-factor in terms of the structure. But what I really want to focus on in this chapter, one of the main things at least, is how to draw the structures of polymers and the way that I would like you to draw structures of polymers. All right, I'll even say it, the way I would like you to draw structures of polymers on the final exam, should they be there? And I would hope that they are. My hope is, with us spending a class and a half or 2 classes on polymers, I would hope that if I didn't have at least a few things on drawing polymers, you'd be kind of angry, since we spent some time on it. Good. So the simplest and one of the most ancient addition polymers is polyethylene. So, and basically, we're not making polyethylene here, we're making polystyrene, but polyethylene would be the same thing, only even simpler, just with CH2CH2. And think of how many things that we use that are made of polyethylene. It's everything from plastic bags to disposable Tupperware type containers, your plastic bottles, your soda bottles, even the caps are generally made of polyethylene, except that's cross-linked polyethylene. So you can see somewhat different properties in, say, the cap on a soda bottle as opposed to the soda bottle itself. So there can be more than one form of each of these polymers. But other types of others of that class in terms of polymers include polystyrene, which we've discussed, polyvinyl chloride, that's your PVC, you've heard of PVC pipes. Polyacrylonitrile is another one. And these all basically vary depending on what this group is that used to be on ethylene. Of course, if instead of a benzene ring, you have a hydrogen, you just have ethylene and the polymer is polyethylene. If that's a methyl group, then you've got propylene, which makes polypropylene. If you've got a benzene ring, then of course you've got yourself polystyrene, which we've talked about. I'll probably use polystyrene for the next several examples of the types of polymers that we go over. Replace that with a chlorine, you've got polyvinyl chloride. Oh, and if you replace 2 of the hydrogens of ethylene with chlorines, then you get polyvinylidene chloride. And there's actually a vinyl chloride, vinylidene chloride copolymer. I think that's saran. So that your saran wrap, you know what that is. You can go to the store and buy that. And of course, if you these are only a few of them, but if you replace, instead of a benzene ring, instead you have a nitrile functional group, then you've got polyacrylonitrile. Well, because the monomer is called acrylonitrile, so you get polyacrylonitrile. And polyacrylonitrile finds lots of uses. I mean, I'm not a big expert on materials, but I know that it's extremely resistant to tearing. I think polyacrylonitrile is used in it. I could be wrong about this. I thought polyacrylonitrile or something similar was used in, you know, those types of envelopes that you can't tear. I think that might have polyacrylonitrile or something like that in there. Certainly polyacrylonitrile is going to be, and the reason I mentioned, where did I mention it being in the carpets in the room? Yeah, so even the carpet in this room. So I doubt that's true of the carpet in your room unless you're on campus. But sort of your industrial strength carpets that you would find in lecture halls in the university, or if you go to the airport, you know, the industrial strength carpets, those are largely made of polyacrylonitrile, and they're very, very resistant to wear and tear. Good. So since the polymer chain will contain all of the atoms of the monomer, see, you've got 2 carbons, 3 hydrogens, and a benzene ring. So there you go, 2 carbons, 3 hydrogens, and a benzene ring. When you draw the structure of the polymer, you want to reflect that. You want to show what is the repeating unit. And this is the way that, well, that's the way I was taught to draw polymers, which I think is a pretty good way to do it. And we'll expand on this method of drawing polymers when we get to condensation polymers next time. But notice how I'm doing this here, that you've got all of the atoms in the repeating unit within the parentheses. By convention, we put n here to show where n is just this arbitrarily large number. And we're just showing that this repeating unit repeats an arbitrarily large number of times. could be thousands, tens of thousands, hundreds of thousands, even millions of times. And so as long as you include all of the atoms that are in the repeating unit exactly once, that's the key. As long as you do that, you're in good shape. The only one that might be an exception to that is using that logic, you could draw polyethylene just with CH2 in the parentheses, taken n times. And I can't say that's wrong, but usually we like to draw two CH2s in the repeating unit. And of course, you could condense this if you want. If you want to go CH, and then write CH2 instead of C with HH like that, of course, it's fine. And I mean, you could put the benzene ring anywhere. It doesn't have to be at the top left. Could be here, could be here. Anything like that, as long as all of the atoms in the repeating unit are within the parentheses exactly once, you're in good shape. That's a perfectly good way of drawing the polymer. So I know there are some OWL questions that if you do it slightly differently, but this is the way that I'd like you guys to focus on drawing polymers. I think it's the clearest, and it's also the most consistent way of us to do that. So what is the mechanism for forming something like polystyrene from styrene? Well, generally we need some kind of radical initiator in order to get it started. Usually that's some sort of organic peroxide or hydroperoxide. And so the initiation step would show the peroxide, of course, breaking at that really weak oxygen-oxygen bond and getting two peroxy radicals. The propagation step, I'll get to in just a moment, and the termination step would involve two long chain radicals combining to make an even electron species, just like we did back in chapter 11. Speaking of vowels, I don't see a mastery. We're not doing any for 31, quite possibly not. Generally, these last ones are not graded. And so I would say if you notice that it says not graded, or if the OWL assignment is flat out missing, then that's what it is. But I've already put up all of the OWL assignments, so you don't need to worry about my surprising you with OWL assignments. Anything that I have that exists, you guys already have. So you can consider that as partly making up for if we have to have any multiple choice questions. I feel terrible making any changes to format, but it just might be necessary. Because as you know, with final exams, there's a hard deadline by which I have to have grades calculated. If it didn't really matter until if I had them, sometime in June or something, that'd be fine. And that's how it used to be, I think, in the old days, like when I was in college. But no, there's a hard deadline. Naturally, this term I missed the hard deadline for midterm grades, which is the first time I've ever done. Luckily, I was in compliance because I just needed to let you guys know what your grades were, some way that was what's the word? Anonymous. So I had done that. That was available on eCampus. Good. Oh, by the way, since it looks like we're all going to Canvas next term, good luck with that. I got kind of run over by a train several times getting used to Canvas with my Chem 227 class. And in fairness, there are things that are better than eCampus. One thing that's kind of cool, to the extent that you'll have any online grading, and I think even if it's not online grading, I believe it calculates averages automatically. So so that's kind of cool. But there are things that are different. In Chem's high school and EM2 school, I've got everything. Yeah, well, I kind of got blindsided by a lot of things. That was part of my problem also with grading, especially. It's the only good thing is gives you the average. Well, I don't know. There's some things that are better from my perspective as the professor. One thing is if I want to move columns around, I can just literally grab and drag them. So it doesn't crash as much. I believe that, yeah. In fact, we were having problems with eCampus just the other day. Anyway, back to polystyrene. So I've shown you here what the mechanism would look like for the propagation step. It's going to start with this peroxy radical, or whatever it is you're using as your radical initiator. that's going to react with a molecule of styrene. I'm using styrene just as an example. This could be any alkene here. And you get an organic radical with this, again, little peroxy or ether cap over here, if you will. That's going to find another molecule of styrene and react and find another one, and on and on and on it goes. You can see you're going to build up this long chain. And I think you'll have to agree, if you're fair about it, that the resulting polymer has this structure. Yes, you do have this ether group over here, but if this part here repeats 50,000 times, then I think the little groups capping it at the end, I think you'll have to acknowledge they're a non-factor. They don't matter in comparison to the large bulk of the structure being repeated styrene units. And so that just goes on and on and on until you start to run out of styrene, and then the reaction will terminate. Again, by, let's say instead of this having happened 2 or 3 times, this has happened 30,000 times. Well, at some point along the chain, there's a radical that's going to find some other one that's repeated 28 or 30,000 times, and the 2 radicals will find each other and join together, and you'll get a single polymer chain. And so that's how the reaction terminates. But other than that, I think this mechanism that you see here is no different really than what we did back in chapters 6 and 8 or 6 and 7. So that's how polystyrene is born. That's how polyethylene is born. Polyacrylonitrile, PVC, any of these other ones that are cousins of polyethylene. That's basically what the mechanism of that looks like. That's how it's usually done anyway, in terms of with a radical reaction. There are other ways of making addition polymers. There are also cationic and anionic variants, which I mentioned in the class notes, but I didn't show you guys. So I have them over here kind of ready to go. With a cationic polymerization, now you're not going to use a radical initiator. Instead, your initiator is to be some kind of Lewis acid. It could even literally be a Bronsted-Lowry acid. I suppose I could have used an HCl molecule. For some reason, a bit of boron trichloride or boron tribromide came to mind, and you could certainly do it that way too. And the difference is now, of course, we're going to be using full arrows when we draw our mechanism. None of these tedious half arrows. So your alkene will react with the boron halide or H plus or whatever it is that your initiator is. And now instead of getting a radical, now you'll get a carbocation. And so sure enough, that carbocation is going to find another styrene molecule. That styrene molecule will add to the carbocation and make another carbocation, which another styrene molecule will come along and add to it, and on and on and on it goes. Eventually, you're going to run out of styrene, and then the reaction will terminate just by deprotonating next door to wherever the carbocation is. Something will come along, maybe a halide ion or something, if there's nothing better to act as the base, will come along and pull that proton off, and you'll get maybe a double bond at the far end of one of the molecules. And again, apart from these little capping groups that can be different, or am I having a case of the Mondays? That would be the Mondays, yes. Remember, boron's a funny atom, and really the entire column, because boron is an exception to the octet rule, right? When it's in its neutral state, it is only 6 electrons around it. It can take on a 4th electron pair and have 8 electrons around it, but then if you work it out, the formal charge is -1. So boron's never happy. That's why it has its characteristic reactivity. That explains hydroboration, that explains sodium borohydride, and so many other things. So in this particular case, Mason, I would say it's the Mondays, which the Mondays plus the last week of the term, plus God knows what else. So I don't think anyone blames you for that. But yes, the formal charge is correct. Boron will have a charge of -1. And again, whether it's boron or some other group over here, and even if we have an alkene at the other end, again, the overall structure of the polyethylene is going to, polystyrene is going to be the same. These little bits that you have on the end, if this business repeats tens or hundreds of thousands of times, they're inconsequential. They don't have any real they're not even worth mentioning in terms of the overall structure. But you can make addition polymers by cationic polymerization too. And like I said, it's generally self-terminating. You just need to deprotonate. There is even more rarely used something known as anionic polymerization. And that turns the whole idea on its head. In this case, what you need is some sort of nucleophile to get the thing started. It could be a little bit, we did a polymers lab in my previous school where we did an anionic polymerization, and the initiator was sodium hydride, or maybe it was even potassium hydride. Geez, I was terrified. That stuff is just a fire waiting to happen. Yet somehow, I don't know how, there was never a fire all the years I was there. But you could use a little bit of that. You could use a little bit of some alkyl lithium or Grignard reagent. Anything that can act as a good nucleophile will do. And in this case, your nucleophile, in this case, it's a carbanion, right? It's butyl minus, will attack the monomer, and you'll get, wait, did I do that right? Yes, I did do that right. And you'll get a carbanion. That carbanion will go and find another molecule of your monomer and attack that, which will make a carbanion, and sure enough, that will find another molecule of the monomer and attack that, and you'll make another carbanion, and on it goes. The difference is this guy is not self-terminating, because you're always going to have another carbanion, and there's always going to be, or at least there at least for a while is going to be a double bond somewhere that the carbanion can attack. And so this will still make your polymer, but this we have to terminate at some point, generally by adding a little bit of water or maybe an alcohol, something protic, in order to quench any remaining carbanions by adding a proton to it. The overall structure of the polymer, again, will be the same. It's just a question of how long are your polymer chains going to be before the thing terminates. So trying to think if there's anything else, but the mechanism in this case relies on carbanions for anionic polymerization, as opposed to carbocations with cationic polymerization. And notice again, in both these cases, we're using normal, ordinary, full arrows in our mechanisms. These are not radical reactions. If I just want to go back to the cation, oh, I think I just did. Yup. Now, my understanding, I am no polymer chemist, but my understanding, I read your mind, how about that? My understanding of the situation is cationic polymerization is used only rarely, and anionic even more rarely. But since anionic polymerization isn't self-terminating, they sometimes call these living polymers, which is kind of creepy. But and again, I could be wrong. I certainly don't have my finger on the pulse of the industry. But my understanding is radical polymerization is used probably, if you absolutely had the proverbial gun to my head and I had to make a guess, I would make a conservative estimate they use radicals at least 80% of the time. That would be my guess. But these other methods also exist and can make addition polymers. Doesn't really affect the structure. The only thing that might change is the length of the polymer chains, which will of course affect the properties of the polymer as well as its structure. But I think the general idea behind all of these in terms of getting addition polymers is the same. You wind up getting addition polymers this way. Could there be any potential benefits to using cationic or anionic over radical? You would think there ought to be. It might affect the structure, because we're not, I do have one more thing at least that I want to talk about. It might have to do with the form of the polymer that you get, whether it's, as we're about to get into, atactic, syndiotactic, or isotactic. It might affect that. Other than that, I can't really say that I know. I mean, if I were in charge of the thing, I don't really trust radicals, to be honest. My instinct would be to favor cationic polymerization. By the way, that's how Bakelite was made, through kind of a cationic process. So they've all been around for many, many decades. But I'm afraid the simplest answer I could give you about potential benefits, I don't really know. I just am not familiar enough with the industry. I bet, however, that YouTube would know, and I bet you could find some interesting things. I'm sure there is an effect on the overall structure or properties, I should say, of the polymers that you get out. I'm sure that matters, but I just am not familiar enough with the nitty-gritty. Sorry. Let's see. Good. So let's see. The other thing, I already talked about copolymers for a bit, so I think that's enough. I just wanted to say another issue of these types of addition polymers is that they're not all created equal, unless you're talking about polyethylene, which is going to be achiral no matter what you do. As soon as you replace one of those hydrogens on ethylene with any other group, whether R is a benzene ring to make polyethylene or a cyano group to make polyacrylonitrile, phenyl group, of course, makes polystyrene or polyacrylonitrile, PVC, whatever it is that you're making, all of a sudden you're introducing chiral centers. And there are 3 flavors of polymer chains. One possibility, which I think is the easiest to make, is one in which there's no ordering whatsoever of those side groups in the polymer chain. They're just at random, so to speak. And we call that type of polymer chain atactic, A, the prefix meaning not. It's also possible to get polymers such that all of those chiral carbons have the same configuration. They're either all R or all S, and we call that type of polymer chain isotactic. And then the last possibility is it's possible to make these so that they alternate, RS, 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 and that's called a syndiotactic polymer. Those of you going on in materials will no doubt talk about these in more detail. Mostly, I just wanted to get those terms into your, on your, at least on the far side of your radar screen, so you're aware of them. But certainly they all differ in properties. If I were to ask you, of these 3, which would you guess would be least crystalline, wild guess, I think you would all guess that the atactic would be least crystalline, and you'd of course be absolutely right. Same thing, if we would expect isotactic and syndiotactic polymers being more regular in structure to be more crystalline. My understanding of the way you make isotactic and syndiotactic polymers is it requires special catalysts, which on the one hand are really, really, really expensive, probably involving rare earth metals or other uncommon transition metals. The bright side being, of course, it's a catalyst, so you need relatively little of it. But that's the only other thing I really wanted to say about addition polymers, and we can leave condensation polymers until next time. Step growth or condensation polymers. Those are fun. I think you'll enjoy those. Those will be your nylons, your polycarbonates, your polyesters, things like that. Those are, I find those really fun to talk about. So, and again, I don't think I'm going to have to teach you anything new in order for you guys to understand those. So with that, let's see, we have 7 minutes left. That should be plenty of time to do a couple of brief questions. Good, so you guys can be thinking if you have any other questions. Other than that, with your cellular telephones, if you please. Let me move this over here. I'll do a slideshow. Actually, well, should I include? Yeah, I guess I'll include this in the video. I can always cut this down if need be. Okay, so question 1. Let me move everything out of the way, including my weird face over here. The following conversion takes place during the citric acid cycle, which is the best description of this reaction. Let me flip this over to polling. And I would put it to you that one of those 5 is right, the other 4 ain't. So you want to pick the one that is and none of the ones that ain't. Is the final open note? I believe so. Yeah, I think the final is going to be just, we aren't going to change the format that much. I think the final will be just like the hour exams, except there will be more time. I should also say the final will be considerably less than twice as long as the hour exams. I usually aim to make my final exams doable in about an hour and a half. I certainly don't plan on people needing all 2 hours. Some people take it, and you're welcome to it if you want it, but I don't think you'll need it. At this point, since I might have only just one grader, I might have to think about making the length shorter rather than longer. So we'll just have to see how it goes. I will try to cajole at least 2 graders into coming back. Okay, well, what I'm seeing when I'm going from succinate to fumarate, I don't see anything involving water. It's not like we lost water to make the double bond, so it's not a dehydration, but we certainly did go from a carbon-carbon single bond to a carbon-carbon double bond, so we've increased the bond order. That looks to me like an oxidation. Another way of thinking about it is that we have more carbon-hydrogen bonds in the starting material and fewer carbon-hydrogen bonds in the product. So that's another way of looking at it that convinces me that we're looking at an oxidation. So I think A is the best answer. And so did you, just barely though, but we'll take it. Okay, last but not least, the following reaction takes place during glycolysis, which is the best description of this reaction, same thing. And this is really the way I'd like you to think about the chapter 29 material. I wouldn't say this is all of it, but I think this is the main type of thing I'd like you guys to focus on. Certainly, I don't care if you memorize the names. Your biochem prof might care, I don't. Okay, so hopefully what you're seeing here is it might be tempting at first to say it's an oxidation because we're going from a secondary alcohol to a ketone. But we're also at the same time undergoing reduction of an aldehyde to a primary alcohol. So those two cancel each other out. This reaction is overall neither oxidation nor reduction. Certainly there's nothing involving water. I don't see hydrolysis generally means water being added or water, again, the Greek roots mean loosening by water or breaking apart by water. Nothing like that is happening. There's no loss of water or indeed of anything else. All you're doing is going from this molecule to something with the same formula, but a different structure. In other words, an isomer. So I think isomerization is the best answer here. And this goes through that all-important enediol to go from the aldose to the ketose, from glucose to fructose. So I think the best answer is D, as did you. Good, and I think with that, oh, look, oh, geez, it was exactly 11:30. I was gonna brag on myself a little bit. Good, so we are out of time. And hey, I got through it without falling asleep, so hooray for all of that. So with that, I will see you all on Wednesday for our last class. Have a great day, and like I said, expect today, tomorrow, I should be able to get you your official exam 3 scores. Oh, and I should say I'm aware that exam 4s need to be graded for sure by Thursday, since Friday is the deadline for Q dropping, which I don't think affects most of you, but it is on the minds of some of you. So we're certainly going to do our very best to get those finished by Thursday. I'm not sure how, especially if I still have only one grader, but we'll do. Actually, in fairness, the grader that quit already did his part on exam 4. So we should be relatively easy to make whole. So other than that, see you all on Wednesday and have a great day.